We have just seen that undergoing a phase change can be affected by both temperature and pressure. We can combine all that information for a substance into what we call a phase diagram. And that's what we're going to talk about in this section, phase diagrams. If we go into the laboratory and we actually take a substance and we vary the pressure and the temperature, and we measure the temperature and pressure under which a substance undergoes a phase change, we can actually put all that together and actually create a phase diagram. So phase changes and the relationship with temperature and pressure are depicted in a phase diagram. So in a phase diagram, we typically plot temperature on the x-axis and pressure on the y-axis. So if we look at this phase diagram, each of the different phases is actually separated by a solid line. So everything at this temperature and pressure shown in this light area, gray area here, is a gas. Everything that is in this slightly darker area is actually a liquid, and everything in this dark gray area here is a solid. So depending on the temperature and the pressure, my substance can either be a solid, a liquid, or a gas. And there's a special point here which we're going to talk about shortly. It's called a supercritical fluid. So in other words, if I change the temperature at a constant pressure, I can actually go from a solid to a liquid. I keep on raising the temperature. I go over to a gas. If I start over here in the gas phase and I start to reduce the temperature at a constant pressure, I condense the material into a liquid, and finally I freeze it over into a solid. At certain pressures and temperatures, I can actually go directly from a gas. So for example, if I'm sitting down here, I'm at this pressure and this temperature, and at a constant pressure, I start to actually lower the temperature. I can actually just start to deposit my material or go from a gas to a solid. If I'm sitting over here at a constant pressure and I heat the material up, I can actually go over to a gas. And the opposite is true. If I sit at a constant temperature and I start to raise the pressure, I can convert that gas into a liquid. If I'm sitting at a certain temperature down here, I go from a gas and go directly over to a solid. And if I'm sitting here at a constant temperature and I start raising my pressure, I can actually convert my liquid into a gas. So you can see how useful a phase diagram is. So I can measure what temperature and what pressure I have to actually have one of my three different states of a material: a solid, a liquid, or a gas. Let's use the phase diagram to the right to actually interpret some of the different important points on a phase diagram. What's the melting point of this substance at 1 atmosphere? So let's see, I'm here at 1 atmosphere. And what is melting again? That's actually going from a solid to a liquid. So here's my 1 atmosphere. I want to go from a solid to liquid. That would be point A here. And what temperature is that? I just come down here, and that's approximately 140 degrees. Can I also determine the boiling point at 1 atmosphere? So what is the boiling point? That's the point at which I go from a liquid to a gas. So at 1 atmosphere, I come over here, I'm a liquid, and here I go at point B here, I go from a liquid to a gas. I come down here, and the temperature is 200 degrees. So this substance actually boils at 200 degrees C at 1 atmosphere. Let's also now find out what is the physical state of a substance at 2 atmospheres and 110 degrees. So at 2 atmospheres, I'm going to come over to 110. That's point C here. So my substance at this temperature and pressure is actually a solid. What phase transition occurs when I go at substance X here, I go from 2 atmospheres at 110 degrees. Let's see, 2 atmospheres, 110 degrees, and I heat the substance up to 200 degrees. So I heat it up to 200 degrees, I go from a solid to a liquid. That's melting. Now at point D, what if I then reduce the pressure to 0.5 atmosphere, so I can go down on the phase diagram here to 0.5 atmospheres, and I reach point E here. And that is actually vaporization. So I'm going from a liquid to a gas when I go through from D to E. Let's also use this at what temperature is sublimation possible? That's actually going to be point F here. That is actually the minimum temperature that I can actually have on which I can actually sublime a material. So if I come over here, that's approximately 115 degrees. At any temperature above that, I cannot sublime the material. When we look at a phase diagram, there are actually some terms that are associated with a phase diagram that are important. When you see the word normal, that implies that we are at 1 atmosphere. So if we look at the phase diagram here and look at 1 atmosphere, this is the normal melting point at 1 atmosphere. This would be the normal boiling point. There are also a few other terms. The critical temperature. The critical temperature is the temperature beyond which a gas can no longer be liquefied. So if I look at this point right here, if I keep on increasing the temperature, I can no longer create a liquid up here. So the gas can no longer be liquefied. In this case, for this example, it's 374.4 degrees C. At that same point, a critical point, there's actually a critical pressure. That's the pressure beyond which a liquid can no longer be vaporized regardless of the temperature. So if I'm sitting at this pressure, I can no longer vaporize the liquid. At that point, in this region up here, above the critical point, I can no longer create a liquid or a gas. We call this a supercritical fluid because the state of matter is sort of neither a liquid nor a gas. There is also a term which is associated with the point at which all 3 phases coexist. That is the point right here. That's the point where we can have a solid, a liquid, and a gas all coexisting at the same temperature and the same pressure. Let's identify all these areas on the phase diagram for CO2. Let's first look at the normal point. So we come down here to 1 atmosphere. We notice that this normal point here would either be the deposition normal point or the sublimation normal point. How about critical point? The combination of temperature and pressure beyond which a gas cannot be liquefied, that's going to be up here. That's the critical point. The critical temperature is going to be 31.1. The critical pressure is going to be 73 degrees. The supercritical fluid region, again, is going to be up here in this region right here. And the triple point will be right here at a pressure of 5.11 atmospheres and minus 56.4 degrees Celsius.